Okay, so very good. So we are ready for the next talk today. So Luis Polanco with the title Data-Driven Torsion Coordinates and Wasserstein Stability.
Good morning, everyone. Thanks to the organizer for the invitation and opportunity to give this talk. So I'm gonna start by giving a little explanation of the core idea behind the work that I'm gonna present here. So let's say that we start with a data set, let's say sample around a circle with noise. We wanna take topological features out of this data set, and we wanna find maps of this data set into quote unquote interesting spaces. And what interesting is gonna be for us or for me during this talk is gonna be lens spaces. And on that note, let me remind you real quickly what a lens space or the model that we're considering for lens spaces. So we're just thinking of them as quotients of odd dimensional spheres by the right action of a cyclic abelian group, which is CQ. And the important thing that I'm going to use about lens spaces, or one of the important things that I want you to keep in mind, is that I'm going to use a specific model for low dimensional lens spaces, specifically for LQ2. And the model that I'm going to focus on is the one that I'm describing here. Is given by a ball in R3 with identifications on the boundary. And the identifications are given by take a point on the boundary, make a rotation of 2 pi over q radians, and then reflect against the x1, x2 plane. And let's please keep this model in mind, because all the results that I'm gonna, or a lot of the figures that I'm gonna present later on are gonna be using this model to a greater extent. So how do we go from topological features to obtaining quote unquote interesting maps into lens spaces? So to do this, we're gonna use the Brown representability theorem, which, just as a reminder, on the left-hand side, we have cohomology of a CW complex with coefficients in an abelian group. And on the right-hand side, we have homotopy classes of maps onto Eilenberg-MacLane spaces. And just as a quick reminder, the Eilenberg-MacLane space, KGN, is a topological space who has homotopy concentrated on degree n, and the homotopy group corresponds to a group G. So, and the basic idea is that we're gonna take a cohomology class, and out of that, we're gonna construct a classifying map that is gonna take our base space B into one of these Eilenberg-MacLane spaces. And depending on the different combinations of ends and groups that we take, we obtain different types of what we're calling coordinates. So for example, for n equal 1 and g equals c, the corresponding Eilenberg-MacLane space is the circle. So we will call these circular coordinates because we're mapping our base space into a circle. For n equal 1 and the group C2, we obtain real projective coordinates, and so on and so forth. And the one that we're gonna be focusing on for this specific talk is the last case that I have here, which is n equal 1 and CQ for Q prime, which is gonna give rise to lens coordinates, as we're gonna be obtaining maps into lens spaces. So this is the tool that is running in the background. So how do we go about actually obtaining this map out of one of these cohomology classes? So first of all, the setting that we're gonna use is that we're thinking our data sets just as finite metric spaces. Out of these, we're gonna select a collection of landmarks. And since we're in a metric space, we're gonna consider an open core or data set given by metric balls in this specific case. And using this information, I should point out that the base space B, in this case, this is the W complex that we're going to be using, is going to be the nerve of U. That's the space that we're going to be working with. And on top of that, we're going to need partitions of unity subordinated to this specific core. And since I'm mainly interested in computing things specifically, I'll need to provide like a specific partition of unity. And if you look at this, this is an explicit example of a computation, like of a partition of unity that you can compute. You can throw this into a computer after choosing some weights, omegas. If you want some intuition of what this partition of unity looks, you can think of this just as little cones above each landmark, and they just cut the plane on the corresponding ball, on the corresponding metric ball. Using this partition of unity, we can construct this specific incarnation of the classifying map that I mentioned before. One of the things that I want to point out about this specific incarnation is that we have explicit expressions for the partition of unity that I just gave you. And in this case, CQ is just the cubed root of the unity. So this is an explicit expression that we could almost take to a computer. The only step that is missing is that we need an element, like we need a cocycle on the nerve. The problem is that is in principle hard to compute, but here's where we are going to have use or leverage the fact that we have interleavings between the ribs and the check complex or the nerve or the nerve of the core that we're using. And the way that we use it, is by obtaining this map. So if we want to obtain a non-zero class in here, we just need to take a class in the ribs on the ribs filtration that lives long enough across the cohomological filtration, so that we're sure that when we map it to a nerve, we have a non-zero class. And that's basically what this is telling us, is that we can use basically Ripser to obtain classes in the right place that we want, to actually be able to compute explicitly, this expression for the classifying map that I just described. So one drawback of this is that if you pay attention to the way that I describe this map, it is high dimensional, and the dimension n corresponds to a number of landmarks that I selected at the beginning. So this raises a question: can we solve this high dimensional problem? So can we develop some type of dimensional reduction procedure for these coordinates? And the answer is yes. And the idea is actually fairly simple. So since we're thinking or we're looking at length spaces as quotients of spheres, we can think the dimensional reduction that we're going to make is inspired by how one would do dimensional reduction in a sphere. So let's imagine that we have a data set on S2, like I show here. The idea of dimensional reduction is to find the S1, the maximal circle in S2 that best approximates that data set. And that comes to a question of finding a plane such that when I intersect that plane with S2, it gives me the quote unquote best approximation. I have to make explicit what I mean by best. And that question about finding a plane is just a question about finding the normal direction. So if we keep that in mind, I can rephrase the problem of, or we can rephrase the problem of dimensional reduction of finding a proper direction. So given a data set on a length space, the question that I want to answer is, how do I find an adequate direction that defines a length space of one dimension less in such that we obtain the best possible approximation? And by best approximation, we mean we're trying to minimize the distance in the length space. One of the things that I want to point out is that this minimization problem that we want to solve is nonlinear, however you see it. Like, not the restrictions nor the objective function. But, I forgot to mention, yeah. But we can actually approximate this problem quite well, like with this linear approximation. And what this linear approximation should be telling you is, oh, this is just like the standard PCA solution, if you want to think about it that way. So once we have this information at hand, let's look at some examples to see how this looks in practice. So let's start with the example that I gave at the beginning. So I have a data set that is sampled around a circle with Gaussian noise in the normal component. I select 10 landmarks. I compute persistent cohomology of the landmark set. And using this, I use the classifying function that I define. I compute lens coordinates, and then I do dimensional reduction. What I'm showing here is basically how much information in terms of the distance you're losing at each step of the dimensionality reduction procedure. So you see that at the right-hand side of this, of the graph on the right, we have, it starts at, or the endpoint is 10 because I have 10 landmarks. What I'm showing you is how much distance information you're losing as you move towards lower dimensional lens spaces. And what we see is that somehow what we would expect is that if you go all the way to n equal 1, which should be L13, again, should be just a circle, it'll recovers almost all the information that we want in terms of distances. So how does this map look? And again, here's where it comes the specific model for L32 that I talked at the beginning. So, and what we see that we have here is like a little wire inside the ball, and it is only touching the boundary of this ball in R3 on the yellow points. And we have to remember then the identification that we have, and it's a 2 pi over 3 rotation, and then a reflection against the XY axis. So this, in fact, is a circle embedded in an interesting way inside this low dimensional lens space. Let's look at a more complicated example. So let's take the Moore space C31, which is just, again, is a CW complex that has homology concentrated at degree n. One can describe this space as take a disk in R2, and let's give identifications to the boundary of the disk. And then the identifications are given by these 2 pi over 3 rotations. And that's what the colors signify here. So if you realize the colors correspond to thirds of the circle, and I'm thinking of those, of keeping that identification only in the boundary. So we take the landmarks, we compute persistent cohomology. In this case, I'm doing it with both coefficients in C2 and C3, just to check that I'm actually obtaining a space with the correct topological properties. Then we compute lens coordinates, we do dimensional reduction, and this is, again, the profile of a curve of cumulative variance in terms of distance that I obtain. And again, as we see, as we would expect, like we recover like almost 70% of the information for L32. And how does this map look? Which is the interesting thing. And it looks like this. And what we see here, I want to point out, is that basically what we are obtaining is a disk inside of the ball, and the identifications that we have at the beginning are taken care by the identifications on the boundary of the ball. And what this is, or one of the interesting things about this specific example is that we start with a space, and we had that we define in R2, and we have to keep track of some identifications. But when we map it into L32, like we can't forget the identifications because they are taken care by the space itself that we're mapping into. So it is, in that sense, it is making it easier to keep track of what the space actually is. One rational question about all of this is we jump through a lot of hoops to obtain this dimensional reduction algorithm and these coordinates into arguably complicated spaces. So how does this fare against other standard like dimensional reduction algorithms? In this case, I choose Isomap because it's a fairly standard algorithm that whose aim is to preserve distances as much as possible. So what do we have here? So what we have here is basically, I take my space, I compute length coordinates, I do dimensional reduction until L32, which is a four-dimensional space. And then I do the same thing for Isomap. I go down to the same dimension, and I compute persistent cohomology. And what I'm doing is I'm taking the most persistent and the second most persistent classes in H1, and I'm computing the quotient between their lifetimes. And this is basically telling me is how far away the most persistent class is from the cluster of other classes that you should expect to see in this case. And what this result is telling us is that our algorithm or our length coordinates are able to preserve the topological information that methods like Isomap may be losing in the process of the dimensional reduction. The same thing was done for like the initial space was the length space L32, and we obtained similar results in the quality of the length coordinates after dimensional reduction. So once this is settled, then we can ask questions about, okay, how stable is this procedure of computing length coordinates? So to answer this question, let's say, okay, I start with two different landmark sets, and I'm gonna assign some weights to these landmark sets, and I'm gonna think of this just as probabilities into the landmark sets, such that the infinite Wasserstein distance is small or is controlled somehow. And with this in mind, we obtain the following result. Basically, for a given resolution alpha, and a given, I can choose a class in the diagram of the Ripser of one of the landmark sets. Then I can find a matching class, and the matching is, if you think how the matching it's obtained, it is obtained through matchings that are used to compute this Wasserstein distance, or it is controlled by one matching that should realize this inequality. So we can find this specific class, and we can define isometries from these length spaces that, if you think about it, have different dimensions, because in principle L and L tilde could have different sizes, and I can map them isometrically with some restrictions into LQ infinity. And what these isometries allow me to do is to basically take the data set in both length spaces, map them into L infinity, and then compare those two data sets into LQ infinity. And the result that we obtain is that it is controlled in this manner, that is basically controlled by the Wasserstein distance and controlled by this beta R function, that if you want to get an intuition of what it is, you can think of it as a multi-scale comparison of probabilities, how the probabilities change for the different landmark sets. So as I move landmark sets and I change resolutions around alpha, how are these probabilities that I'm defining, how different they are? That's a rough intuition of what this term is basically telling us in this theory. But aside from looking scary, let's see how this behaves in some examples. Before that, like if you look at this, I said, okay, we should define some weights on the landmark sets. I didn't say how, and it is kind of open. So let's see the effect that could have into our coordinates. So what I'm doing here is I'm taking two different sampling strategies, maximum sampling and uniform sampling. And by uniform, I just mean using the distribution of the data set. I sample the landmarks using the same distribution. And I define the weights. What I'm doing here is I take the weight one. If I have 100 landmarks, the way that I put is 1 over 100 for each landmark. So it is the same weight all across the landmarks. And that's not the only way that I could do it. I could do adaptive weights. And what I mean by adaptive is take your landmarks, draw some metric balls around them, and define a weight that is related to how many points are contained in those balls. And this is an attempt to capture, like if I have an isolated point, it should weigh a little, but if I have a point that is in a really densely populated region of my data set, it should weigh a lot, or that should be the intuition around that. And I can do it in different manners. So the adaptive weights is just, the first one is just fix the radii, and the second one, the locally adaptive, is I allow the radii to change for each landmark, if that makes sense. And if I compare across all these examples, what we obtain is that what seems to happen is that, so for example, for uniform sampling, it seems that the preferred weighting strategy is the uniform one, while for maximum sampling, the preferred strategy is adaptive weights. And what this somehow is telling us is that the weights that we're assigning to the landmarks should somehow resemble the underlying distribution or the empirical distribution of the data set. So this is kind of the intuition of what this example is telling us, how the weights should be or could be selected to obtain good quality maps. And what can we use, or where could we use like this stability, for example? Let's say that we start with a huge landmark selection, and we would like to reduce the landmark size, the size of the landmark set. We can do it like take your landmark set, do some clustering, and replace each cluster of points each cluster of landmarks by its center of mass, and weight that center of mass by adding the weights all in the same cluster. Like if you think about it, like in Wasserstein, in the Wasserstein distance, those two landmarks should be really close. And that is the reflection of that fact. It is seen here in that the maps themselves that we obtain even after doing dimensional reduction are really close. And what we gain with this type of landmark simplification procedure is we gain a lot of computational time. Because we think of what we are doing here, we need to compute persistent homology, we need to compute coordinates, and we need to do a huge dimensional reduction procedure. And what we see here is that we have almost a 50% of reduction in computation time, and it is highly concentrated on the persistent cohomology computation, which for all these examples was done with Ripser. And I just want to clarify that is just because we need to compute generators to compute all this, the classifying map. We need an explicit generator. And with that, I would like to end. There are some references for the bulk of this work.
Okay, thank you. So now I would ask everyone to unmute themselves and clap for Luis and his talk. For question. Yeah, so remember, if you want to ask a question, you unmute yourself and then ask. Okay, so if then I'm going to go ahead and ask. So because you said it's sort of, I mean, the title is data driven. Have you like tried anything on data sets? I mean, sort of not like the ones that you created, like just for testing.
So far, I have not. I have not tested this in any real world data set, but we're in the process of getting there.
Is there, what kind of data sets are you looking at? I mean, like, where do you think that there would be an advantage of taking this, say, over circular coordinates? Like,
so for example, one example that one data set that we have in mind is that we can we can replicate the name, sorry, projective spaces as patches of images. And
okay.
like using that specific, like out of extracting a specific model for patches of images that will resemble a projective space, like circular coordinates wouldn't fit that well because you'll lose a lot of info, like you'll lose the main information of the projective part of the space.
Yeah.
So it is in those type of cases. One example that we have in mind and we're working on is working with configuration spaces. Like if you're looking for if you're looking at configuration spaces, we expect them to have like non-trivial homotopy basically, and in those cases, that's basically what we're trying to capture with this type of coordinates. It's just like data set that may have a lot of torsion in them.